Imagine a place in the universe where gravity is so powerful that nothing, not even light, can escape. This is the realm of black holes, a concept that has both fascinated and terrified scientists for decades. A black hole forms when a massive star undergoes gravitational collapse at the end of its life cycle, creating a region of spacetime with an extremely strong gravitational field. Black holes can be classified into several types, primarily based on their mass. The stellar black holes, which form from the remnants of a massive star, can range from about 3 to several tens of solar masses. Then, we have supermassive black holes, which reside at the centers of most galaxies and can weigh millions or even billions of solar masses. Finally, there are intermediate black holes, a mysterious category that scientists are still trying to fully understand. The first evidence of black holes came from observations of star systems exhibiting peculiar behavior. Astronomers noticed that certain stars were orbiting an invisible object that exuded an immense gravitational pull. This invisible object was later confirmed to be a black hole. One of the fundamental observations regarding black holes is that they are defined by their event horizon. The event horizon is the boundary that marks the point of no return. If anything crosses this boundary, it cannot escape the black hole's grasp. But what happens to objects that fall inside? The journey into a black hole is anything but simple. As matter approaches the event horizon, it experiences extreme gravitational forces. The tidal forces become so intense that they can stretch objects into long, thin shapes, a phenomenon known as spaghettification. Imagine being pulled into a black hole and feeling your body elongate beyond recognition. There is also the notion of time dilation near a black hole. The closer one gets to the event horizon, the slower time moves relative to an outside observer. This means that for someone falling into a black hole, time would appear normal, but for those watching from a distance, it seems to come to a standstill. This strange interplay of time and space raises questions about the nature of reality itself. As we delve deeper into the mystery of black holes, we begin to unravel the complex interplay of physics that governs them. But what really happens to the information about the matter that gets consumed by a black hole? Can it ever be recovered? As we explore these questions, we must also consider the role black holes play in the cosmos. They are not merely cosmic vacuum cleaners, they influence the formation and evolution of galaxies themselves. In the next chapter, we'll take a closer look at how black holes are created and the evidence that supports their existence. The formation of a black hole is a dramatic and violent process. It typically begins with the life cycle of a massive star. A star spends most of its life fusing hydrogen into helium at its core, producing energy that counteracts the force of gravity trying to collapse it. However, once the hydrogen in the core is exhausted, the core contracts under the force of gravity, while the outer layers expand. This leads to the formation of a red giant. If the star is massive enough, the core will continue to collapse, eventually leading to a supernova explosion. This explosion is one of the most spectacular events in the universe, capable of outshining entire galaxies for a brief moment. During the supernova, some of the outer layers are ejected into space, while the core continues to collapse. If the remaining mass of the core exceeds about 3 times the mass of the Sun, it will collapse into a black hole. At this point, a new black hole is born, and it begins to exert its gravitational force on its surroundings. One of the most famous black holes we know of is Cygnus X1, a stellar black hole located about 6,000 light-years from Earth. It was the first strong black hole candidate identified in 1964 and is still actively researched today. The behavior of Cygnus X1 has provided astronomers with critical data about the formation and properties of black holes. Supermassive black holes, on the other hand, are believed to form differently. They may arise through a process of gradual accumulation of mass, stargazing, mergers, or the direct collapse of massive clouds of gas. evidence suggests that supermassive black holes existed when the universe was only a few 100 million years old, hinting at a rapid growth process early in cosmic history. The existence of supermassive black holes challenges our understanding of galaxy formation because they tend to reside at the center of massive galaxies, including our own Milky Way. Their gravitational influence helps regulate the formation of stars and provides insights into the evolution of galaxies. However, there are still more questions than answers regarding black holes. For example, how do they grow so massive so quickly? What is their role in the cosmic web of matter and energy? As we uncover these mysteries, we will explore the evidence that supports the existence of black holes in the next chapter. The challenge of observing black holes lies in their very nature. Black holes do not emit light. Instead, they are inferred through their interaction with surrounding matter. Astronomers have developed various methods to detect these enigmatic objects, including observing their gravitational effects on nearby stars and gases. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves produced by merging black holes. This groundbreaking observation confirmed a major prediction of Einstein's general theory of relativity and opened a new field of astrophysics. Gravitational waves ripple through spacetime, providing us with an unprecedented tool to study the universe. Another significant breakthrough came in 2019 with the Event Horizon Telescope, EHT, which captured the first-ever image of a black hole's event horizon. This historic image showed the supermassive black hole at the center of the galaxy M87, completing a multi-year project that involved a global network of radio telescopes. The image presented a bright ring-like structure surrounding a dark center, representing the silhouette of the black hole. The EHT's findings were monumental, not only because they provided visual evidence for black holes but also because they confirmed key theories about their properties. The size of the black hole matched predictions based on the equations of general relativity. This was a huge step in understanding how black holes behave and their effect on cosmic surroundings. As technology continues to advance, we can expect more remarkable discoveries in the field of black hole observation. New observatories, such as the James Webb Space Telescope, promise to provide insights into the early universe and the formation of black holes. Investigating the cosmic microwave background radiation may reveal clues about the conditions that led to black holes shortly after the Big Bang. With each discovery, we inch closer to unlocking the secrets of these cosmic giants. Yet, profound questions remain. How do black holes warp spacetime? Can they be connected in some way? As we ponder these questions, we must also explore the theories surrounding what happens inside a black hole. One of the most intriguing mysteries associated with black holes is the information paradox. When matter falls into a black hole, what happens to the information that describes that matter? According to quantum mechanics, information cannot be destroyed. However, black holes seem to challenge this principle. Stephen Hawking proposed that black holes could emit radiation, a phenomenon known as Hawking radiation, allowing them to lose mass over time. If a black hole eventually evaporates entirely, what happens to the information within? Does it disappear forever? This question has stirred intense debate among physicists. Some suggest that information is preserved in a holographic manner on the event horizon, encoding the information and allowing it to be retrieved. Others posit that it is completely lost to the universe, violating the fundamental principle of information conservation. This philosophical tension has sparked ongoing discussions about the nature of reality and the laws of physics. Recent research suggests potential resolutions to the paradox, such as the idea that information may escape black holes through quantum entanglement or that it could be stored in subtle correlations in Hawking radiation itself. These ideas are still heavily debated and far from conclusive but indicate that black hole physics operates uniquely compared to other realms of physics. understanding the fate of information in black holes also has implications for our overall understanding of the universe. If information is indeed lost, it may challenge our concepts of causality and the nature of space and time. As we explore these complex ideas, we must ask ourselves, can we ever truly know what happens inside a black hole? What does the future hold for our understanding of these cosmic enigmas? Black holes play a pivotal role in the structure and evolution of our universe. While they are often perceived as destructive forces, they are also key architects of cosmic architecture. At the centers of most galaxies, supermassive black holes act as gravitational anchors that help regulate star formation in their surrounding regions. Research indicates that galaxies and their central black holes grow together, as the black hole's gravity influences the motion of stars and gas within the galaxy. This process creates intricate interactions that shape galactic dynamics, leading to the formation of beautiful spiral structures and other formations observed in galaxies today. The balance of matter around black holes is essential for the life cycle of galaxies. Moreover, black holes are not solitary beings; they can merge and collide, producing immense energy that can be detected across the cosmos. The merging of two black holes releases energy equivalent to several solar masses in the form of gravitational waves, which can travel across vast distances. These events are not only significant in understanding black holes, but they also provide insights into the laws of physics themselves. The influence of black holes extends beyond individual galaxies. They are thought to be connected within vast cosmic webs, influencing the distribution of matter and energy throughout the universe. Some scientists theorize that black holes may be gateways to other dimensions, adding another layer of complexity to their role in cosmic evolution. In the broader context of the universe, understanding black holes allows us to glean insights into fundamental questions about time, space, and the origins of the universe. As we continue to study these enigmatic objects, we unravel the history of the universe itself. As we wrap up this journey through the complex interplay of black holes in our universe, we are left to ponder, how much more is there to discover? What awaits us beyond the boundaries of our understanding? As we journey deeper into the enigma of black holes, we encounter a term that sends shivers down the spine of even the most seasoned physicists: spaghettification. It's a chilling concept that describes what happens to objects as they approach the event horizon of a black hole. Picture this: an astronaut, bravely venturing close to a black hole, is suddenly caught in the immense gravitational pull. What happens next is nothing short of extraordinary. Spaghettification occurs due to the intense gravitational gradient present near a black hole's event horizon, the boundary beyond which nothing can escape. The force acting on the feet of the astronaut, which are closer to the black hole, is significantly stronger than the force acting on their head. This difference in gravitational pull stretches the astronaut into a long, thin shape, much like spaghetti. This process is not an abstract concept. It is a phenomenon that, in theory, applies to anything venturing too close to a black hole. In 1976, physicist David K.G. O'Brien calculated the limits to which stars could be stretched before they disintegrated completely, an insight that shed light on the fate of cosmic matter in these extreme environments. Spaghettification isn't just theoretical. It's a vivid illustration of the power of black holes and their ability to warp space and time. For instance, consider the destruction of stars that orbit too closely to supermassive black holes at the center of galaxies. As they spiral inward, they are pulled apart in what is known as tidal disruption events. In 2014, astronomers observed a tidal disruption event in the galaxy SDSS 121012. The star was ripped apart by a supermassive black hole with a mass of about 1.6 billion times that of our Sun, creating a brilliant flare as its remnants were consumed. The implications of spaghettification extend beyond just terrifying imagery. They offer insight into the fundamental forces of nature and the resilience of matter. Understanding how different objects react under extreme gravitational forces can help us comprehend the nature of black holes themselves. Yet, one must wonder, what if we could go beyond this fate? What mysterious realms lie beyond spaghettification, beyond the event horizon? As we ponder these questions, we're reminded that black holes are not merely cosmic vacuum cleaners. They are gateways to exploring the laws of physics at their most extreme. But what happens to matter once it crosses that event horizon? Can it ever return? This question leads us into our next chapter, where we delve deeper into the nature of black holes and the fate of information within and beyond their grasp. We've just uncovered the horrific fate awaiting anything caught in the grasp of a black hole, spaghettification. But there's another profound mystery that continues to baffle scientists: the fate of information. What happens to the information about the matter that vanishes into a black hole? This most perplexing question is at the heart of what is known as the black hole information paradox. Theoretical physicist Stephen Hawking introduced this paradox in the 1970s, positing that black holes emit radiation, now termed Hawking radiation, which causes them to lose mass over time and eventually evaporate. However, the crux of the paradox lies in what occurs during this process. If a black hole evaporates completely, where does the information about the matter that fell in go? According to quantum mechanics, information cannot be lost. Yet, if matter is completely consumed by the black hole, information about its state seems to vanish. Imagine a scenario, a thought experiment. If you throw a book into a black hole, the information contained in its pages should somehow persist. But once it crosses the event horizon, it appears to be irrevocably lost. Numerous scientists have tried to reconcile this with formidable theories in physics, leading to heated debates. In 2007, a groundbreaking paper proposed a new perspective: information might not be lost but rather preserved on the black hole's surface, encoded in the event horizon itself. This notion aligns with the holographic principle, suggesting that the universe can be described by information defined on a distant boundary. The debate has passionate advocates on both sides, with some like Leonard Susskind defending the idea that information is not lost, while others, including notable physicist Andrew Strominger, push for interpretations that maintain black holes as information sinks. As we probe this mystery, it ignites deeper questions about the nature of reality itself. If information truly cannot be lost, then what does this imply about the structure of the universe? What if the key to understanding black holes lies in reconceptualizing our understanding of information itself? Next, we'll explore how black holes might inform our understanding of the fundamental laws of physics, shedding light on the universe's most profound mysteries. As we continue our exploration, we arrive at a fascinating revelation: black holes are not just cosmic monsters, they play a critical role in shaping the very structure of galaxies. These enigmatic entities influence their surroundings in ways that are only beginning to be understood. The presence of supermassive black holes at the centers of galaxies correlates with various structural features of galaxies. Research shows that nearly every large galaxy contains a supermassive black hole, including our own Milky Way. These colossal structures can exert substantial gravitational influence, regulating star formation rates in their host galaxies. When gas and dust come too close to a supermassive black hole, they can be heated to extreme temperatures, producing outflows and jets of material that can either stimulate or suppress star formation. For example, in the galaxy M87, the active supermassive black hole generates jets of particles that extend thousands of light-years into space. This dynamic interaction between black holes and their surrounding environment highlights a duel between creation and destruction. Moreover, the gravitational waves emitted by merging black holes can provide insights into the history of galaxies. Detecting these waves allows scientists to trace the growth and evolution of black holes and their host galaxies, revealing a deeper connectivity within cosmic structures. In fact, the LIGO Observatory has detected multiple black hole mergers, shedding light on the interplay of mass and gravitational forces over cosmic time. As we ponder the implications of these cosmic forces, we realize that black holes serve as both the architects and the executioners of galactic evolution. What mysteries lie ahead as we explore how these colossal entities connect to the very fabric of spacetime? This convergence of black holes and galaxies takes us to our next chapter, where we will discuss the possibility of black holes being gateways to other realms. Throughout history, black holes have sparked the imagination of scientists and laypeople alike with their potential to serve as portals to other realms. The idea that a black hole could lead to another universe or dimension is a tantalizing possibility that invites speculation about the very nature of reality. Theoretical physicist Kip Thorne has long championed the idea of wormholes, hypothetical passages through spacetime that could connect distant parts of the universe, or even different universes altogether. These structures, if they exist, could be traversable, allowing for rapid travel across cosmic distances. However, the relationship between black holes and wormholes remains a point of contention among physicists. Is it possible that black holes could serve as entry points to wormholes, or are these ideas purely speculative? In the context of the multiverse theory, the notion of black holes leading to alternate realities is even more intriguing. Some interpretations of quantum mechanics suggest that each decision we make spawns a new universe, creating branches of reality. Could black holes be the means through which we could access these other universes? If so, what might we find on the other side? What kind of beings or civilizations might exist in those realms? While these theories require robust mathematical frameworks, recent research, including that conducted at the Event Horizon Telescope, has strived to better understand black hole physics. As we stand at the cusp of understanding these cosmic phenomena, the question remains, are black holes merely cosmic graveyards, or are they keys to a greater universe? Prepare yourself as we approach the final chapter of this extraordinary journey, where we will reflect on the implications of our findings. As we draw our exploration to a close, let us contemplate the future of black hole research. With each advancement in technology, scientists inch closer to unveiling the deeper mysteries hidden within these enigmatic structures. The advent of gravitational wave astronomy has revolutionized our understanding of black holes. Observatories like LIGO and Virgo are at the forefront, detecting the faint ripples in spacetime caused by black hole mergers. These breakthroughs have not only confirmed general relativity but also opened new avenues for studying black holes and their role in the universe. For example, the Event Horizon Telescope captured the first-ever image of a black hole, providing visual evidence of their existence and spurring on an era of black hole imaging and study. What's more, future missions such as the James Webb Space Telescope are set to explore hotter, denser regions of space, potentially uncovering new black hole candidates and further illuminating their significance in cosmic evolution. The growing collaboration among international space agencies promises to magnify our observations and deepen our collective understanding. But beyond observational breakthroughs, the theoretical landscape of black holes continues to expand. Researchers are proposing novel ideas in quantum gravity, string theory, and the interplay between black holes and fundamental forces. As we ponder the implications, one thing is evident: black holes are not merely cosmic curiosities, they hold the key to understanding the universe at its most fundamental level. Will we one day traverse a black hole and emerge in another realm? As we conclude this documentary, let us embrace the mystery and wonder that black holes bring to the cosmos. They challenge our understanding, inspire curiosity, and remind us that the universe is still an unfathomable tapestry waiting to be unraveled. Together, as we continue to explore the wonders of the universe, let us remain vigilant in our quest for knowledge. The journey into the heart of black holes has only just begun. When we think of black holes, we often imagine dark voids in space, consuming everything in their path. However, the effects of black holes reach far beyond their immediate vicinity. These enigmatic objects play a critical role in the cosmos, influencing the formation of galaxies and the very fabric of spacetime itself. They are not simply cosmic monsters but vital players in the universe's grand narrative. Black holes come in various sizes, from stellar black holes formed through the gravitational collapse of massive stars to supermassive black holes residing at the centers of galaxies. Each type exerts a unique influence on its surroundings. Stellar black holes, for example, can alter the paths of nearby stars through their immense gravitational pull. One striking case is that of Cygnus X1, a well-studied black hole in the constellation Cygnus, which is pulling material from its companion star, creating X-ray emissions that can be detected from Earth. Supermassive black holes, on the other hand, are often found at the cores of galaxies. The Milky Way hosts Sagittarius A*, a supermassive black hole with a mass 4 million times that of our Sun. Its gravitational influence governs the orbits of stars and gas clouds near the galactic center, shaping the overall structure and dynamics of our galaxy. But the impact of black holes extends even further. They are believed to be the engines that drive the feedback processes within galaxies. When matter falls into a black hole, it heats up, and this energy can be released in the form of jets, powerful outflows of material that can influence star formation in the host galaxy. This interaction illustrates how black holes can trigger or suppress star formation, a cosmic balancing act where creation and destruction coexist. One of the most dramatic examples of this phenomenon occurred in the galaxy M87, home to one of the first black holes to be imaged by the Event Horizon Telescope. Observations revealed not just the black hole itself but also jets extending thousands of light-years into space. These jets are thought to influence the growth of surrounding galaxies, providing a stunning demonstration of how black holes actively shape the universe. Moreover, the gravitational waves produced by colliding black holes have opened a new window in understanding the cosmos. Since the first detection in 2015 by LIGO, scientists have captured numerous events involving merging black holes. Each merger provides valuable information about the nature of gravity, the formation of black holes, and the dynamics of the universe. These discoveries reinforce the significance of black holes within the cosmic tapestry. As we continue to study these fascinating entities, we uncover more about their role in the growth and evolution of galaxies. By piecing together the data from gravitational waves, X-ray emissions, and stellar dynamics, we are beginning to understand the intricate dance between black holes and their host galaxies. This synergy raises profound questions about the future of galactic formation and the ultimate fate of the universe. Will black holes continue to shape galaxies as they grow, or will they evolve into something altogether different? As we delve deeper into black hole research, the answers may very well redefine our understanding of the cosmos. As we venture deeper into the mysteries of black holes, we arrive at one of the most perplexing and iconic features, the event horizon. This boundary marks the point of no return, where the gravitational pull becomes so intense that not even light can escape. Understanding the event horizon challenges our very notions of physics and reality. What happens beyond this threshold remains one of the greatest enigmas in science. The concept of the event horizon is rooted in Albert Einstein's theory of general relativity, which describes how mass distorts space-time. As objects approach a black hole, they experience extreme gravitational effects, which can warp time and space in ways we struggle to comprehend. Imagine watching a clock ticking as someone descends into a black hole. From the distant observer's perspective, time appears to slow down for the individual falling in, stretching out until it seems to freeze at the event horizon. But from the falling person's perspective, time continues normally until they cross the threshold. This raises the question, what happens to someone who crosses the event horizon? Is there a point at which they cease to exist? Or do they continue to exist in some form within the black hole? Some physicists propose that information does not simply disappear but becomes encoded in the fabric of the black hole, an idea that we will explore further. The very nature of reality could be at stake as we delve into concepts like black hole complementarity and holography. The study of event horizons has significant implications for our understanding of the universe. For example, the existence of an event horizon implies that information is fundamentally altered, challenging the traditional view of causality. This paradox contributed to the infamous information paradox, where black holes seem to violate the principles of quantum mechanics. Stephen Hawking famously suggested that black holes could emit radiation, later termed Hawking radiation, which allowed information to escape, albeit in a very scrambled form. But if information can escape, how does it do so? Is it possible that the fabric of spacetime becomes altered, creating alternative pathways for information to be recovered? This elusive idea leads us to think about black holes as not only destroyers but also as potential gateways to understanding the universe at a fundamental level. Could they provide insights into quantum gravity or even the unification of the four fundamental forces? Moreover, the study of the event horizon connects with the continued exploration of scientific boundaries. Physicists and astronomers are working together to advance our knowledge through telescopes, particle colliders, and theoretical models. As we strive to comprehend the complexities of black holes, we must also consider the broader consequences for our understanding of the cosmos. The very data we gather may help unravel the mysteries surrounding dark energy and dark matter. The event horizon thus serves as a stark reminder of how much we still need to learn about black holes and about the universe itself. As we stand at the brink of understanding the event horizon, we may soon find that it holds the key to many of the fundamental questions we have about existence. Why is the universe structured the way it is? And what lies beyond the veil of black holes? The implications of our discoveries could change everything we think we know about the cosmos. As researchers dive deeper into the enigma that is the black hole, the intersection of quantum mechanics and general relativity becomes increasingly significant. Traditionally viewed as distinct realms, quantum mechanics governs the behavior of subatomic particles, while general relativity describes the cosmos at a grand scale. Black holes sit at the crossroads of these two frameworks, leading to profound questions about the nature of reality itself. The conflicting principles of quantum mechanics and general relativity emerge vividly in the context of black holes. On one hand, general relativity posits that nothing can escape a black hole once it crosses the event horizon. On the other hand, the principles of quantum mechanics suggest that information cannot be lost. To illustrate this clash, consider the fate of matter and information entering a black hole. According to quantum mechanics, every particle carries information. However, general relativity suggests that once something falls into a black hole, that information is destroyed, leading to the infamous information paradox. This paradox is a point of contention among physicists, as it challenges the core foundations of both theories. The intriguing concept of entanglement offers a potential resolution. When two particles become entangled, the state of one instantly influences the state of the other, regardless of distance. Some theorists propose that black holes could entangle particles with the information stored at their event horizon, allowing for information to be preserved even as it appears to disappear. This hypothesis suggests the possibility of recovering that information later, perhaps through Hawking radiation. Moreover, recent developments regarding black hole thermodynamics have further blurred the lines between quantum physics and general relativity. According to this theory, black holes possess entropy and temperature, linking them to thermodynamic principles in an unexpected manner. This idea leads to the notion of black holes behaving like thermodynamic systems, raising profound implications for our understanding of entropy and information flow in the universe. One fascinating case study comes from the work of physicists like Juan Meldacena, who proposed the holographic principle. This theory postulates that our three-dimensional universe can be represented as information encoded on a two-dimensional surface, placing black holes at the center of this hypothesis. If true, this could mean that our understanding of spacetime is fundamentally flawed. The holographic principle invites us to reconsider our perceptions of reality and challenges the very nature of existence. As we continue exploring the intertwining of quantum mechanics and black holes, we uncover a world of potential discoveries waiting to be made. The development of new technologies, like quantum computers, may offer the tools needed to approach these ancient questions from a fresh angle. By harnessing computational power to model black hole behavior, researchers could potentially unlock some of the darkest secrets of the universe. The role of quantum mechanics in unraveling the mysteries of black holes emphasizes the need for interdisciplinary collaboration within the scientific community. Breaking down the silos of physics could lead to groundbreaking advancements in our understanding of the cosmos. The journey toward uniting general relativity with quantum mechanics remains one of the most formidable challenges in modern science, yet it is a pursuit that could fundamentally alter our worldview. As we grapple with these profound concepts, we may soon find that black holes are not merely cosmic objects of destruction but instead, gateways to understanding the fabric of the universe. Will we unlock the secrets held within these enigmatic objects, and in doing so, rewrite the laws of physics as we know them? As we plunge into the heart of a black hole, we encounter a perplexing question: what happens to matter when it crosses the event horizon? This boundary, which marks the point of no return, raises more questions than it answers. The moment matter crosses this threshold, an enormous gravitational force begins to stretch and compress it dramatically. Here, we delve into the terrifying concept of spaghettification, a term coined to describe the violent tidal forces exerted on objects nearing a black hole. Imagine the Earth itself being pulled into a black hole, stretched into a long, thin strand of matter akin to spaghetti. This interaction highlights not just the physical destruction of objects, but the intricate dance between gravity and material. In the vicinity of a black hole, the rules of physics become increasingly bizarre. According to general relativity, the gravitational field of a black hole is so powerful that it warps spacetime to an unimaginable degree. Matter, which would normally behave predictably under Earth's gravity, becomes subject to extreme conditions that can only be theorized about. Consider the case of a hypothetical astronaut who ventures too close to a black hole. As they approach the event horizon, their body would be subjected to differing gravitational pulls on their head and feet, resulting in disintegration long before reaching the singularity. But what about the ultimate fate of the matter? What happens to it once it crosses this boundary? The current scientific consensus suggests that it is crushed into an infinitesimally small point at the center, the singularity. Here, the laws of physics as we know them cease to function, leading to paradoxical implications and leaving scientists struggling to understand how to reconcile general relativity with quantum mechanics. Theories abound, but many remain speculative. Further explorations into black holes reveal that they don't just destroy matter, they might also transform it. Recent hypotheses suggest that the information within matter could somehow escape the black hole, either as radiation or through alternative channels, challenging our understanding of information conservation in physics. Throughout history, black holes have been framed as cosmic destroyers, yet a new narrative suggests they could be the universe's recycling bins. As we ponder these deep secrets of black holes, we realize that our quest for understanding leads to equally profound questions about existence itself. Ultimately, as we grapple with these cosmic enigmas, we inch closer to uncovering the secrets of the universe, and perhaps even ourselves. As we delve deeper into black holes, we find ourselves navigating the perplexing realms of quantum mechanics, a field that challenges the very fabric of reality. Quantum theory suggests that at its core, the universe is governed by probabilistic events rather than deterministic laws. This starkly contrasts with the predictable nature of general relativity, where gravity reigned as the unyielding arbiter of cosmic events. One of the most intriguing aspects of black holes lies in their relationship with quantum information theory. When an object crosses the event horizon, what happens to the information that describes that object? This conundrum, known as the information paradox, left physicists bewildered for decades. It challenges our understanding of what it truly means for information to be conserved in the universe. To put it simply, if information can be lost when entering a black hole, it implies that the fundamental laws of physics could also be violated, undermining our grasp of reality itself. Renowned physicist Stephen Hawking suggested that black holes might not be as impenetrable as once thought. He proposed that black holes could emit radiation, a phenomenon now known as Hawking radiation. This radiation would allow black holes to leak information in a slow, gradual manner, possibly resolving the paradox. But the implications of this theory extend far beyond mere black hole mechanics. If Hawking radiation effectively allows information to escape, could we reconcile the behavior of black holes with the principles of quantum mechanics? Moreover, if black holes can emit radiation, they might eventually evaporate entirely, a result that begs the question of what happens to the information they contained. In this context, the idea of black holes being windows to the quantum realm emerges. Some physicists theorize that black holes could be pathways to alternate realities or different states of existence. Could they serve as bridges between worlds? These thoughts echo through the annals of theoretical physics, inspiring a new generation of scientists to explore the complexities and mysteries of the universe. Ultimately, as we delve into the quantum enigma of black holes, we recognize that the path to understanding is filled with uncertainty and wonder. Each exploration of the black hole not only illuminates the cosmic stage but also reflects our quest for deeper knowledge about reality itself, leading us back to fundamental questions that have perplexed humanity for centuries. Black holes have long captivated the collective imagination, and at the heart of this fascination lies a tantalizing question: could they function as cosmic time machines? As we consider the manipulations of spacetime induced by extreme gravity, we begin to entertain extraordinary possibilities, a reality where time might bend and twist in ways previously thought impossible. Einstein's theories suggest that gravity can warp spacetime, curving it to such an extent that it could theoretically allow for time travel. The concept of closed time-like curves arises when discussing black holes, proposing that if one were to navigate around a black hole's rotating event horizon, they might find a pathway that loops back in time, creating a dazzling, albeit speculative, journey into the past. However, the notion of time travel powered by black holes comes with its own set of paradoxes and challenges. The physical laws governing the universe dictate that causality, the relationship between cause and effect, must remain intact. If one were to alter events in the past, it raises complex scenarios surrounding paradoxes such as the grandfather paradox, where a time traveler might inadvertently prevent their own existence. Moreover, the conditions near a black hole are so extreme that only the most advanced technology could possibly approach them, let alone survive. Even if we could traverse time through a black hole, the perils of spaghettification loom ever large, challenging the safety of any mortal explorer. Yet, the allure of black holes as time machines remains a tantalizing topic for physicists and philosophers alike. Speculations abound, and new theories continue to emerge, suggesting that these cosmic entities might be fundamentally linked to the nature of time itself. As we grapple with these profound questions about the nature of time, we recognize that black holes serve not only as windows into the cosmos but as mirrors reflecting our own aspirations, fears, and curiosities about existence and reality. The journey through the mysteries of black holes leads us to ponder our place in the universe and opens pathways into uncharted waters of understanding. When we gaze into the night sky, we see countless stars, each holding its own unique story, yet there exists an unseen force that influences the very formation of galaxies, the supermassive black hole. It is an awe-inspiring fact that nearly every large galaxy has a supermassive black hole lurking at its center. These titanic structures can weigh millions to billions of times more than our Sun, and their existence has profound implications for the structure and evolution of galaxies throughout the universe. But what exactly is the role of these behemoths in galactic evolution? To grasp their significance, we need to dive deep into their properties and the mechanics at play. Let's start with one of the most studied examples, Sagittarius A*, the supermassive black hole located at the center of our Milky Way galaxy. This enigmatic entity has a mass equivalent to approximately 4 million suns, yet it remains invisible to the naked eye, shrouded in clouds of dust and gas. Research into supermassive black holes reveals that they do more than just exist, they actively shape their galaxies. The gas and dust swirling around a black hole forms an accretion disk, a hot, luminous disk of material that spirals inward, emitting vast amounts of radiation. This process creates extreme conditions, leading to the ejection of powerful jets of energy and matter, often referred to as active galactic nuclei. Such phenomena have been observed in quasars, distant galaxies powered by supermassive black holes. The radiation from these jets can regulate star formation within the host galaxy, meaning the very presence of a supermassive black hole can dictate the fate of its surrounding stars. Interestingly, the relationship between supermassive black holes and their host galaxies appears to be one of mutual influence. The mass of the black hole correlates with the properties of the galaxy itself, including the mass of the stars and the distribution of dark matter. For instance, studies show that the mass of a galaxy's central black hole is closely linked to the velocity of stars in the bulge of the galaxy. This indicates that during their formation, galaxies and their central black holes evolved together, a phenomenon known as coevolution. This intricate dance raises many questions about the early universe. Did galaxies form around these black holes, or did the black holes form first, drawing in gas and stars? One compelling theory suggests that the seeds of supermassive black holes could originate from the collapse of massive stars shortly after the Big Bang. These primordial black holes would grow over billions of years, absorbing surrounding material and merging with other black holes, leading to the supermassive black holes we observe today. This evolutionary path might explain why we see a correlation between the size of black holes and the galaxies they inhabit. For instance, the largest supermassive black holes, such as those found in giant elliptical galaxies, could have been shaped by more frequent mergers and interactions with other galaxies, resulting in immense gravitational pull and rapid growth rates. The implications of supermassive black holes extend far beyond the confines of their galactic homes. They play a crucial role in the cosmic web's formation, influencing the distribution of matter in the universe. As galaxies interact and merge, the gravitational forces at play can lead to the formation of new stars and even trigger bursts of star formation, vastly altering the galactic landscape. Conversely, the energy expelled from these black holes can suppress star formation, leading to quiescent galaxies. As researchers continue to unravel the mysteries of supermassive black holes, they uncover more about the universe's evolution and structure. For example, the Event Horizon Telescope's groundbreaking imaging of the shadow of M87's supermassive black hole provided insights into how these giants influence their environments. Such observations are crucial in piecing together the history of our universe and understanding the fundamental forces shaping it. With every advance, we come closer to understanding not just the life and times of supermassive black holes, but also their profound connection to the galaxies harboring them. In conclusion, supermassive black holes are not mere cosmic spectators. They are dynamic entities influencing the life cycles of galaxies and the universe as a whole. Their gravitational dance contributes to cosmic evolution, making them essential players in our understanding of the cosmos. But this leads us to a thought-provoking question: what lies at the core of a supermassive black hole, and are there deeper mysteries waiting to be unveiled? When we think about black holes, we often imagine the swirling darkness and the gravitational pull that can consume everything, light included. However, what lies beyond the event horizon, the boundary that separates our observable universe from the unknown? The event horizon is not just a point of no return, it is the gateway to a realm where the laws of physics as we know them start to break down. In this chapter, we explore the enigma of the event horizon and what secrets it may hold. To understand the implications of crossing the event horizon, we need to grasp what happens to matter and light when they enter a black hole's grip. Imagine yourself falling into a black hole. As you approach the event horizon, time itself behaves strangely. Due to the intense gravitational field, time dilates, meaning that for an outside observer, you would appear to slow down and almost freeze at the event horizon. However, for you, the experience would be different. Once you cross the threshold, you would find yourself in a vastly different realm where conventional understanding no longer applies. At the event horizon, the escape velocity exceeds the speed of light, creating a one-way trip into the unknown. Once you cross this boundary, nothing, neither matter nor information, can escape back to the observable universe. But what happens to you beyond? Theories abound, and physicists have proposed various models to depict the interior of a black hole. One prominent conjecture is the concept of a singularity, a point where matter is infinitely dense, and the gravitational forces overwhelm all other forces of nature. This idea leads to significant questions and challenges existing theories, particularly general relativity. At the singularity, space and time may cease to exist as we understand them, leading to paradoxes that scientists are still trying to resolve. Do we merely cease to exist, or does some aspect of our consciousness persist? Another intriguing theory proposes that instead of a singularity, there may be a new form of spacetime emerging within a black hole. This idea suggests a creative twist on our understanding of the universe, that black holes are not destructive voids but rather gateways to alternate realities or dimensions. Some physicists speculate about wormholes, hypothetical passages through spacetime created by black holes, potentially leading to other parts of the universe or even other universes altogether. Notably, theoretical physicist Kip Thorne has discussed the possibility of traversable wormholes which could allow for the passage of matter and energy. While initially as speculative as science fiction, advances in quantum gravity may lend new insights into these ideas, blurring the lines between possibility and reality. If true, such phenomena would profoundly impact our understanding of the universe's structure, connectivity, and the nature of time itself. A further layer of complexity arises when we consider the fate of information. Does it vanish forever upon crossing the event horizon, or is there a mechanism that preserves it? Physicist Stephen Hawking famously proposed the notion of Hawking radiation, suggesting that black holes can emit radiation and perhaps allow for the faintest escape of information back to the universe. This has sparked debates around the so-called information paradox. How can information be lost in black holes when the laws of quantum mechanics dictate that information cannot be destroyed? The implications of these explorations extend beyond theoretical physics. They can influence our understanding of consciousness, time, and even the universe's origin. By studying what lies beneath the event horizon, we catch glimpses of the universe's deepest mysteries. Black holes may represent the ultimate frontier, the final destination for knowledge seekers who wish to peer into the unknown. As we seek answers, we must also acknowledge the limits of our current understanding. While the science of black holes is still evolving, the quest to unravel their secrets inspires curiosity and wonder. Each theory, each experiment pushes the boundaries of what we perceive as possible, and within that exploration lies the essence of scientific discovery. In conclusion, while the event horizon might symbolize the end of our journey, it also signifies the beginning of new questions and cosmic possibilities. Are black holes gateways to other dimensions, or do they hold the keys to the fabric of reality itself? As we continue to ponder these deep questions, we realize that the quest for understanding black holes is also a quest for understanding ourselves in the universe. At the intersection of black holes and the fundamental laws of physics lies the search for a theory of quantum gravity, a unified framework that reconciles general relativity with quantum mechanics. For decades, physicists have grappled with this challenge, and black holes, with their unique properties, offer crucial insights into the nature of the universe. In this chapter, we will examine how black holes serve as laboratories for testing our understanding of quantum gravity and how they may unlock the deepest secrets of the cosmos. To appreciate the significance of this quest, we must first understand the gulf between general relativity and quantum mechanics. General relativity describes the gravitational forces that govern large-scale structures, such as planets and galaxies, while quantum mechanics deals with the behavior of subatomic particles. These two theories work remarkably well within their domains, yet they are fundamentally incompatible when confronted with extreme environments such as those surrounding black holes. One of the key insights into black holes comes from the study of Hawking radiation, a phenomenon that suggests black holes can emit particles and slowly evaporate over time. Proposed by physicist Stephen Hawking in the 1970s, this groundbreaking theory bridges the gap between thermodynamics, quantum mechanics, and general relativity. If black holes can emit radiation, they may not be as eternal as once thought, raising questions about information loss and the fate of matter that falls into them. This led to the famous information paradox: how can information be lost when it must be conserved according to quantum principles? Researchers such as Juan Meldacena have explored potential resolutions